So good evening. My name is Nikolaos Papendreou. I am a researcher at the IBM Research Lab in Zurich. And in this talk, I would like to present you our work on demonstrating low latency access to phase change memory in OpenPOWER systems using CAPI. So the objective of this project is to demonstrate phase change memory attachment to OpenPOWER servers via CAPI, and in particular to showcase the efficiency of CAPI protocol in data access from non-volatile memory, and also leverage the low latency and small granularity access of PCM. And moreover, to build a platform where future PCM chips can be attached to OpenPOWER servers via CAPI and tested on real workloads. This work is a joint work between the teams at the IBM Research Zurich and the University of Patras in Greece, and you see the names of the members in the slides. So in the next slides, I would like to present the prototyping system and the non-volatile memory chip that we have used in this demonstration. I will describe the FPGA architecture of the phase change memory controller that we developed and present measurements on latency and performance. And finally, I will summarize the talk. So our prototyping platform consists of two systems, the IBM Power System S812 and the Tian Palmetto Custom Reference System. Both are CAPI enabled. They are running Ubuntu 15.10 and they are equipped with FPGA cards from Alpha Data. With the Xilinx FPGA, which integrates the CAPI, the PSL for the CAPI, and our custom AFU and phase change memory controller. In addition, we built some custom prototype phase change memory DIMMs in order to connect them directly to the FPGA card, and I will describe more details in the next slide. So in this work, we designed two different phase change memory controllers for two different phase change memory technologies. The first one, which is shown on the left, corresponds to an old phase change memory technology using legacy parts from Micron. This is an SLC phase change memory chip with a serial interface. And on the figure on the left, you see the custom PCM DIMM that we built with this particular chip. And also we designed special SODIMM adapters in order to connect this PCM DIMM to the FPGA cards on the server. The second controller corresponds to a next generation phase change memory technology. And here we assume a DDR3 compatible interface, and we used read and write latencies that correspond to state-of-the-art PCM chip designs. Since these parts are not available here for this case, we have used DRAM modules and special hardware to emulate the PCM channel read and write latency and expose the PCM chip characteristics to the host. This figure shows the high-level overview of the FPGA architecture. On top is the CAPI-based phase change memory controller. The custom AFU provides the interface with the CAPI and implements WED and data management. The PCM channel controller implements the interface with the AFU, and in addition, it offers low-level memory management and PHY operations. We built two different PCM channel controllers for the two different PCM chips that we discussed in the previous slide. And moreover, for comparison, we developed a native PCI-based design that implements a descriptor-like protocol, and the PCM channel controller is again the same. So here we show some measurements. This figure shows the CDF of the write and read latency that we obtain using 128-byte accesses. And the measurements correspond to the Palmetto system, the CAPI-based phase change memory controller, and the PCM DIMMs with the legacy PCM parts. So we obtain very low write and read latency with mean values of 2.9 and 8.7 microseconds, respectively. And I would like to stress the small variance of the measurements. So in particular, 99% of the reads complete within 8.8 microseconds, out of which 4.5 are due to the serial command and data interface of this particular chip. If we move to the next generation PCM chip scenario, which we have emulated with special hardware, and we assume a fast DDR3-like interface, here we get even better measurements for the latency with mean values of 2.9 and 3.6 for write and read respectively. And again, I want to mention the very small variance of the measurements, and 99% of the reads complete within 3.9 microseconds in this case. In this chart, we measure the write and read system performance for different data block size, and we also compare CAPI and PCIe. we observed that the copy-based controller outperforms the native PCIe design, and we get similar results for both systems S8020 and the Palmetto. And for large block sizes, the system bandwidth basically is limited from the PHY bandwidth of the specific PCM chips, while for small sizes, we can even improve the performance by doing some further optimizations in the data management and the descriptor management at the A view. So, in summary, we have attached PCM to OpenPOWER servers via CAPI and implemented a custom A view on Xilinx FPGA. We designed custom CAPI-based phase change memory controllers, 2 different versions for 2 different technologies. And we measured low latency for 128 bytes read and write access from 2 PCM DIMMs on a power server. As a next step, we are working on improving the performance by doing some protocol optimization at the A view level, and also measure the system performance for different read and write workloads, and also to try to extend the design in order to support multiple PCM channels for higher throughput. Finally, I would like to acknowledge the work of all the people that contributed in this project. Thank you.